Hello everyone, my name is Ryan Butler and I'm the Chief Engineer with Noble Engineering and Consulting, and I'm here today to present an exciting project that we've been working on all year. Noble is a Toronto-based independent firm of engineers, designers, and consultants that work in all aspects of the built environment while specializing in high-rise structures. Our team is comprised of the best and the brightest, and we strive towards exceeding our clients' expectations by finding solutions to their most complex problems, adding value to their projects, and ultimately turning their exciting visions into reality. Noble was retained by our client Jablonski Asim Partners to provide structural engineering and consulting services for the design of a 47-story high-rise condominium. The building consists of 5 levels of underground parking, 8-level podium structure, and a 39-story high-rise structure. The building will be situated at 55 Mercer Street in the heart of the Toronto downtown core. Our methodical approach to design stems from first principle thinking. Industry standard software shown here was used to ensure the needs of our client were met, as well as all code-related requirements. To ensure efficiency and accuracy in our design, complex algorithms were developed for each structural element. This allowed for a streamlined design process and constant communication between team members. Based on preliminary designs, a reinforced concrete structural framing system consisting of lineal and core shear walls was chosen based on cost, practicality, and our client's needs. Structural modeling and analysis was the most time-demanding task. There were very complex architectural specifications involving load transfers, changes in building geometry, and 15 different floor plans over 52 levels shown here. ETABS was used primarily for analysis and to generate loads, while Revit and Robot were used to validate ETABS loads and for detailing purposes. Gravity loads were meticulously calculated based on element dimensions, building occupancy, and building finishes. Wind loads in X, Y, and Z direction were calculated by a wind tunnel and applied to the 24 NBCC wind load combinations. Seismic loads were determined by ETABS while considering 10% eccentricity and accidental torsion. Slab thickness varies between 200 and 250 millimeters based on occupancy loads. One-way and two-way slabs were identified and designed accordingly in SAFE to ensure factored shear and flexural resistance were adequate, as well as crack control. One-way and two-way punching shear checks were also performed. Due to column offsets and parking levels, to maximize parking revenue for the client, high deformation zones were identified and accounted for in our design. Detailing of slabs were also performed in SAFE, and all code-required checks were reviewed. Excel was used to design columns accounting for slenderness effects, combined axial and flexure, and possible tension loads, as there are a number of transfers between shear walls and columns where the shear walls experience tensile stress. Interaction diagrams were developed and checked for each column, and detailing was carried out in Revit, which produced very detailed cross-sectional drawings as well as 3D models of sections shown here. Shear walls were designed using Excel, considering both wind and seismic lateral loads as well as combined axial flexure. The wall thickness ranges from 300 to 600 millimeters, and based on our analysis, tension stresses exist in the top 5 stories, below which there is a pure compression zone which requires only minimum reinforcements all the way down to the 12th floor. Below this, there is a significant change in building geometry, a large wall column transfer, and significant tension stresses again. The ground level elevator core shown here requires only minimum vertical reinforcements, but heavy horizontal reinforcements are required. Noble conducted an in-depth lateral analysis of the building in which code-required stiffness modifiers were applied to cracked and uncracked walls through an iterative procedure shown here, where the stresses in the walls were examined to determine if the modulus of rupture was exceeded. The result is a 10 to 15% increase in the building periods when subjected to lateral loads, and the maximum deflection of the building and the maximum inter-story drifts due to both wind and seismic were determined to be adequate. The foundation of the building sits on shale bedrock with a high bearing capacity, so optimal footing dimensions were determined to be relatively small, but to prevent punching shear, the application of a strut and tie method with compression fan stress distribution was required in design. The result, a total settlement of only 25 millimeters and maximum differential settlement of 19 millimeters. The foundation walls experience relatively small moments due to lateral earth pressure, and as a result require only minimum reinforcements in design. Noble's costing team conducted an in-depth analysis using database-driven software. All direct and indirect costs were considered in analysis, including contingencies, markups, interest, inflation, and even interior finishes. The final cost was determined to be $182 million, which is a savings of over $1 million from our preliminary analysis. With an estimated market retail value of $250 million, this provides the owners with an estimated profit of $68 million. On behalf of Noble Engineering and Consulting, I would like to thank you for listening today and encourage you to reach out and connect with us if you have any questions. Thank you.